All right, welcome to lesson 6, volumes by disk and washer methods. So this would be the same technique we would use to find the volume of the vase from our first day of class. So pretty exciting, we're getting there. This is like kind of the last major new thing that we're learning. The last lesson just has to do with how to change the axis of revolution. So this is the last big idea, guys, yay! All right, so we have volume by disk, and you guys watched the animation on the video I linked, I hope. So hopefully that will be helpful as you try to visualize these problems. The idea is that we take a region here, we have it bounded by the y-axis, the x-axis, and the line x plus 3y equals 6. We take this triangular region, and I want to take it and I'm going to spin it around the y-axis, 360 degrees. And we're going to end up with actually a three-dimensional cone. So pretty cool, huh? To find the volume of the cone, you can use the formula from geometry that they give right here, and that's 24 pi. But of course, it wouldn't be much fun to use regular geometry when we could instead use calculus, right? And the calculus ones will come up. The method will be really handy when we work with shapes that are more complicated, like the vase, which was not so easy to find with simple geometry. Here's how we integrate calculus in here. Notice I have my region here, and they said, what if we cut it into these horizontal strips, make sort of these little trapezoids. If I take and spin that little strip about the y-axis, like I did with my whole region, I end up with a disk, or a cylinder. Now this disk, over here in my region, the distance here was x, right? Wherever my point on my line is, it's just how far away we are, it's the x value. So that's telling me that the radius of my disk is x. My thickness of my disk is the change in y, so that's dy. So my volume of this disk is pi r squared times the height, right? So we have pi, the radius squared, which would be x squared, times the height, which is dy. So you could find the volume by slicing the cone up into these infinite number of really thin horizontal slices or strips. So this is just like a cross-sectional, except instead of us having isosceles right triangles or squares or rectangles, we're actually getting disks. So it's circular regions that we're chopping it up into. All right, actually we're chopping it this way, horizontally. So if we're chopping it horizontally, that means that we have cross sections that are perpendicular to the y-axis. That means we're going to be integrating this with respect to y, doesn't it? Which makes sense since I have a dy happening right here. Awesome. So to find the volume, we are going to go the integral from, they tell us, 0 to 2. And the reason that we're going from 0 to 2, if I go back up to my original picture, you can see the y-intercepts up here at 0, 2. And since these are perpendicular to the y-axis, we're doing all this stuff with respect to y. So that means I care about my y values. And it's going from here at 0 up here to 2. So next would be pi. And then now I need the radius squared, but before we said that was x, I don't want an x in when I'm dealing with y's. We don't want to mix those in. This isn't multivariable calculus. So I need y in terms of x, and so that's when we need to go back to that equation. All right, so if I want to have everything in terms of y, I need to get the x by itself, and so I need to subtract that 3y over. All right, so we have negative 3y plus 6, or 6 minus 3y. This, since this is equal to x, and x was my radius, I'm going to put that here. And the radius is squared in the area of a volume of a cylinder. And then dy just stays dy. So that's how I set up my integral. We can clean this up a little bit to make it easier to integrate. I'm going to pull pi out front. And then the negative 3y plus 6 squared, you guys can do a generic rectangle for that and multiply it out. So go ahead and pause, figure that out. All right, so we end up with 36 minus 36y plus 9y squared dy. Sorry, I didn't have much room there, did I? We'll just cross that out. Okay, so cool. Now we're ready to integrate. So go ahead and pause it and see if you get the same thing I do. All right, so you should get 36y minus 18y squared plus 3y cubed, and we're doing that from 0 to 2. When you work that out, we're going to find that the volume is 24 pi, which we said it should be, right? We did the geometry, and the geometry said volume of the cone was going to be 24 pi. All right, moving on. Maybe. Here we go. I lost my page for a second. I'm good. All right, so it's important to think about what happens to each individual slice or disc as it's rotated around a line instead of thinking about the total volume. So a thin strip or slice could be horizontal or it could be vertical, just like when we were doing cross sections. Remember, the disc method is a type of cross section. So we have, when it's the volume of a disc sliced vertically is going to be V equals pi r squared W, where r is the radius of the disc, W is the width. So keep that in mind. It's always this idea of pi r squared, and W is, normally we would consider it the height, but in calculus it's more helpful to think of this as being the width, dy or dx. So they've got this right here for you to look at. If we have solved for y in terms of x, this is what we're looking at. If it's solved for x in terms of y, this is what we're looking at. Same thing, we just got to pay attention. This one, the bounds are in terms of x. This one, the bounds are in terms of y. And then we either have a dy or dx at the end. Cool. All right, so example 2 through 5, set up and evaluate each integral that gives the volume of the solid by revolving the region around the x-axis. All right, so revolving it around the x-axis. Cool. Always start one of these off with a picture. It will always keep you on the right track. So we have this line, y equals negative x plus 1. That tells me that the y-intercept's up here at 1. And it just so happens that our x-intercept is also going to be at 1. So my line is going here. Oh, that was pretty close. So we end up with a nice isosceles triangle here. So this is our region. Since we could really do this one either way, this way or this way, it's kind of set up to do it. But since they specifically told us to revolve it around the x-axis, that means I'm going to be spinning it like this. If you're not good at drawing three-dimensional pictures like me, mine are super terrible. Usually what I do is I try to reflect this over the line that it's going to be revolved around. And then I just sort of try to pretend that it's 3D-ish looking. So there we are. Okay, so I'm spinning it, which means it's sort of roundish, right? So I'm going to end up with a cone. I know my pictures look terrible. You can laugh. It's okay. You probably need a good laugh today. All right. So notice that my radius is going to be this. All right. So it looks like I'm making vertical strips, right? So all the way down is here, but the radius here is r from here to here. That's my radius, which happens to also be the y value of this line. This part right here, right? This is my radius. All right, so if we're going to integrate this, let's set this up. Volume equals, we'll pull pi out now. Remember, now I'm integrating, I'm worrying about my x because I'm doing this with respect to x. So I need to know my x values. I'm going from 0 to 1. This one, it doesn't matter. They both go from 0 to 1, but it's just a good idea to get into the habit of doing that now. And let's see what else. Oh, we need the radius squared. We already said the radius was going to be this. And then dx is the height or the width of our disk. All right, so we're going to multiply that out. So go ahead and pause this and multiply this out with a generic rectangle if needed. And you should get that you're going to have 1 minus 2x plus x squared dx. All right, go ahead and pause it, integrate it, and see where you end up. All right, and my volume ended up being pi over 3. And again, what kind of units are we dealing with here? Well, they're cubed, right? Because it's volume. So these are units cubed. Awesome. Moving on to the next example. Example 3. All right, so we're going to start off by sketching a picture of what this is going to look like. So if I'm dealing with a square root function, I want to pick values that are pretty easy to work with. The square root of 1 is going to be 1. Zero is 0. And the square root of 4 is 2. So 1, 2, 3, 4. I didn't do this to scale very well, but you get the idea. Up here at 2. All right, draw my graph. Should have a curve to it if we did a better job of drawing than I did. All right, and notice it gave us some bounds here. It says it's bounded by the line from the bounds anyway, from 0 to 4. And it says to revolve around the x-axis. So I'm talking about this region in here. And if I'm revolving it around the x-axis, I'm talking about vertical. I'm going to have vertical pieces here, right? And again, draw your three-dimensional picture, even if it looks bad. Just draw it. Okay, so reflect your point. Okay, and then draw in your picture. Again, not art class. Most of you probably do a better job than I do, but I can tell that I have this round, solid shape. Okay, it's sort of like a rounded cone, I guess would be a good way to put it. Cool. All right, so go ahead and you pause the video, set up your integral, and then unpause it when you're ready and you can see the final answer. Sorry, I'm dealing with limited technology here, so I don't really know how to pause it or cut out the middle of my videos. I'm still working on all this stuff. All right, you should have ended up with 8 pi units cubed. All right, go ahead and try example 4 and 5, and then I will post that video with the answers so you can see them here in just a minute.